So we're going to be doing SVD today, which is singular value decomposition. This is something that I expect all of you to already know, but nonetheless, I'm going to spend most of this class going over the basics of SVD. So for those of you who already know it, this is going to be like a review class. Make sure that you understand it. It's popularly called as the Swiss Army knife of linear algebra, and it's a very powerful tool. It gets used in its many forms. It is a bit of a problem to compute the SVD, the singular value decomposition of a matrix, when the matrix is very large, dense, too large to fit into memory, and so on. And there are ways around it, and that's basically the actual stuff that I would like to teach. These are these randomized versions and special algorithms which are made for computing decompositions, or in the next lecture we'll go a little bit more deeper into randomized SVD, and if time permits we'll go into another concept known as sketching, which is to generate, basically, if you can think in terms of what a sketch would be to a painting, it's to have a smaller approximation, something which is smaller but still approximates the true thing, so the core information is retained. So we'll look at these structures. You need to understand the basic mathematical concepts. So I was not planning to cover the basics, but I will nonetheless. So make sure that you understand it. If you don't, interrupt me wherever you have issues. Okay? So last time we sort of did a recap over recommendation systems and decompositions of the utility matrix into U and V. We looked at gradient descent followed by stochastic gradient descent, and like I said, we're going to be doing SVD today. And this is just a very quick summary of what we were trying to do, was to do dimensionality reduction, wherein that if we had a matrix M, we were trying to decompose it into this U and V form, where both U and V were sort of skinny matrices with the dimensionality reduced. SVD allows you to do this, and we are sort of going to go into how we actually go about doing it in a more formal way. So let's look at it in a more systematic fashion. So assume we are given a matrix A. What SVD does is that it generates this particular form of a decomposition. Keep in mind here, A, I've kept it in the most generic form where it's not a square matrix. Things become a little bit easier when it's a square matrix, but for now, A is an M by N matrix. So we're going to decompose it into a product of three matrices, U and V, which are going to be respectively M by N and N by N, and sigma, which is going to be a diagonal matrix. So this has only diagonal entries in it. And so you can think in terms of, you can write a summation of this form going from j equal to 1 to n, where sigma j, which are the diagonal entries of the sigma matrix out here, and the vectors uj and vj transpose. The sigmas out here are the singular values of A. We'll get a little bit deeper into what exactly that means. The u vectors and the v vectors, which make up basically the matrices u and v, are orthonormal. Do you all understand what orthonormal means? That they are perpendicular to each other in the simplest sense. Mathematically, it's a little bit more complex. And so the u's are the left singular value vectors of A, and v's are again orthonormal when they're the right singular vectors of A. We look at sort of examples of what it means to be a singular vector of a given matrix. You might have covered or studied about or exposed to somewhat closely related problems. The most common thing that you might have experienced is the eigenvalue decomposition, which exists for a square matrix, which is to decompose it into this form of V, some eigenvalues, V transpose. And this is because, and we'll show you what is the exact relationship between an eigenvalue decomposition and a singular value decomposition. Additionally, a very important tool is what is popularly known as a CUR decomposition. In some sense, it is similar to what we did earlier when we did the UV decomposition. What it means is that we are looking for an approximation to the matrix A by having a matrix C which is only a subset of some of the columns of A. So if you think in terms of our recommendation system problem, say that instead of the way we approached it earlier, we say that there are some users, right, who are representative of the general broad sense. So we can model everybody by choosing these. You are a representative user, which means that I retain the row corresponding to you. Similarly, there is an item which is a representative item. Let's say, I don't know, the iPad is a representative of all tablets, let's say. So you can say that I retain the ratings corresponding to that, or maybe an iPad is representative of all Apple products, some sort of a representative. And so I retain some rows and some columns. And that allows me to approximate model A. So we're not generating unique new matrices U and V. We are just generating subsets from the columns and from the rows. And then the task is of which ones to pick and what this matrix U should be so that their individual products give you the matrix A. Have any of you used the COR decomposition ever? No. So maybe we can actually cover that as well. The other thing which is very, very common, especially in science and engineering, is the principal component analysis, which is that you create an empirical covariance matrix given some data, and by computing the singular value decomposition, you sort of try to characterize what the statistical properties of this data are. And we'll take a very simple 2D example, I think in the next slide. The task of finding spanning columns of row, what we just discussed, is again the same idea, and it's related to the singular value decomposition. You can also use the singular value decomposition to have some sort of a relaxed solution for k-means clustering. So you, assuming that your data is now given in the matrix form, you can actually perform clustering by generating the SVD corresponding to this. We've also looked at PageRank, where we talked about the primary eigenvector, the first eigenvector being the PageRank given our transition matrix. Why I'm showing you all of these is that, and this is the reason why these are very different sort of problems and different sort of tools, but having the ability to compute the SVD of a matrix efficiently allows us to generate all of these with minor modifications or with simple changes to the algorithm. Okay, so that's the reason why we want to really focus on singular value decomposition. For go back into this case, you're trying to basically characterize where you have maximum variation. Correspondingly, the singular value, the first singular value, is giving you the spread along this axis for this data. We can actually do something else out here, which is coming back to what we initially wanted to do, which was to get a simpler approximation to what we had out here, which is, the other thing, I forgot to mention this, is that the matrix U times scaled by the singular values gives you the coordinates of the points on the projection axis, so how it would map on to the actual eigenvector space. We can use the singular value decomposition to do a dimensionality reduction, which means that if you take this simple case out here and we say that we want to get rid of the second eigenvector value out here and correspondingly the eigenvector, we can strike this out, basically make it 0, and then you're going to be left with a simplified system out here. In this case, it's only using one eigenvector and one eigenvalue, and what we would get then is an approximation to the original matrix, and you can see here that it's actually zeroed out these values because that's the second mode of variation that you had in your original data. So starting off with a matrix of this sort, we have now generated an approximation by zeroing out some of these eigenvalues and getting rid of those eigenvectors. This is, of course, a very simplified example, but if you look at it a little bit more carefully, you can even think of why, in some sense, this is a clustering of the data that you had. And it has removed this case. Okay?
What does U and V mean? I mean, those are the eigen. Oh, they are the eigenvectors.
Yes. Just wait a minute. I'm going to get a little bit more into detail of what they actually mean. So let's think in terms now of how it's related to an eigenvalue decomposition. Okay? It's very closely related. In general, your eigenvalue decomposition can only be applied to certain special classes of square matrices. But given an SVD of a matrix M, right, we can consider the covariance matrices out here. So if you have M conjugate M, we can expand it out in terms of the singular value decomposition that we have of matrix M. And you are basically going to end up with these structures, whether you consider M transpose M or, sorry, M conjugate M or MM conjugate, assuming it could be potentially complex here. So if we expand it out, because these are orthonormal, these ones are going to cancel out into being identity. The same is the case out here. So you get the structure. Now you can sort of think now when you look at these expansions, you can compare it to a standard eigenvalue decomposition is that the columns of V, if you look at this, are eigenvectors of M conjugate M. Whereas the columns of U are the eigenvectors of MM conjugate, right? And this is important for you to realize that the non-zero elements of sigma out here, the eigenvalues of a matrix, are the square roots of the non-zero eigenvectors of MM transpose or M star M, right? So that's the basic relationship between how your an eigen problem, eigen decomposition of a square matrix is related to the singular value decomposition of a matrix.
Zero values of sigma directly relate to the eigen values of the matrix. Okay.
They're square roots because you see that out here in the eigen decomposition there's sort of been a single lambda out here. So you're basically getting squares of the singular values of M. And you can see it's because also of the fact that we are generating it for MM transpose because we need a square matrix in this case, right? Once we have the singular value decomposition of a matrix, we can actually use it to compute the inverse of the matrix. And try to understand this, why it is important is that, so if you consider here, just for simplicity's sake, that we have A is a symmetric, not symmetric, is a square n by n matrix. So then we're going to have the decomposition where U, V, and sigma are all going to be n by n. Given that U and V are orthogonal, their inverses are just going to be the transpose of each other, right? Because U transpose equal to identity, so U inverse is U transpose, right? Sigma is diagonal. Therefore, the inverse of the diagonal matrix, basically whose elements are, its inverse is going to be 1 over sigma overall, because it's a diagonal matrix.
Because you already taken U as real numbers, only real numbers. Because U conjugate is not equal to U transpose, it's complex.
It's not, yes, in the simple case. In the simple case. So here if you have A transpose, A inverse, then we can write it in terms of having the singular value decomposition and doing this. And you can correspondingly now use this to solve your linear system of equations. One big assumption that we make here is that this is so it depends on the columns or the rows. Yes, it's the same concept again. So in a sense of that, so there are different ways to interpret what you are saying. It's at the fundamental level, it's basically dimensionality. At least from my perspective, the easiest concept is whether this is a good example. If you have something which is, let's say you have a set of points, right? Let's say we are looking at points and they're given as x, y, z, but the z always, again thinking for a simple case, is always 0, right? So you're specifying three-dimensional coordinates. So if you look at the first example where I said you have n by 2, I'm going to have n by 3 now for all the points. It's just that all of them are 0 now. Correct? What it means is that in reality, it's still a two-dimensional data set. It still points, your data is still sitting in 2D space, even though our representation is now in 3D. Now, instead of considering a case where you had x, y, and 0, consider a slight rotation on the space. Okay? So assume that we have, yeah, just say that this is our plane. If we had our measurements such that it was x, y, and this was 0, then you can immediately spot it and you just say I have discarded the 0. So it is a two-dimensional space, which means my representation is now two-dimensional, and it's correct. So the rank is 2. Now if you don't know this in advance, in most of the cases where we are doing this, we are working with very high dimensions and we don't have a true estimate of what the correct dimension is. So again, going back to this 3D and 2D case, imagine if this was rotated now, right? Such that you had, let's say, x, y at 45 degrees, right? Your coordinates, if I show it to you now, is going to look truly three-dimensional. You're not going to be able to make it out. But if you put it in the matrix form, right? Again, thinking in terms of this, again, why do you get this? Because if it's not that we have to make them completely zero, it's just that two of these are the same. With a simple transformation, if I subtract one row from the other, I'm going to end up with zeros, right? Because they are both the same. So if you go back to your basic linear
algebra, plane equation would be perfect, right? Plane equation has dependence over extent, right? And 3 is independent. So if you do on a plane equation, if you take 3 points and then do it, then you'll automatically get the third eigenvalue as 0.
Right, in this case, and that's what you're trying to do. So you can look at it from the perspective of what your the rows and the columns are, and you can think in terms of the two dimensionality that you have in your space. Okay. Now again, think in terms of understanding what the null space of a given vector space now is. So if you think in terms of these, I have defined by this my space, right? So now think of an arbitrary place where instead of x, y, each of this being an identity matrix, you actually, I say that I'm specifying a new orthonormal basis. So these are perpendicular to each other. But instead of being there, it's going to be whatever, minus 1, 1 and minus 1, and this is 1, 1, right? Those are my vectors. Now you can normalize this if you want. If this is the space, so then I'm going to have my vectors out here specified in terms of this, correct? Let's say that z is still 0, 0, 1, right? I can still reach any point in my space by a combination of this. The coordinates now that I specify are not your standard coordinates, but they're going to be coordinates projected onto these spaces that we have, right? So a point that I have in this space is defined by some triplet of values ABC as it multiplies with this, which is basically the projection onto this space. Right? That's giving me what this value is. So when we talk of the range of values, right, that tells me which points in space can be reached by this basis vector. Correspondingly, the null space are the set of points that will give you 0 as the result. If you had a standard Cartesian basis, even rotated in some way, what is the set of values x, y, z that is going to produce a null matrix, null vector? So if you think again, 2D, 3D, whatever dimension you want, what is the set of values if I had a vector space defined by columns of a matrix? What values will give me 0? Think not an arbitrary matrix, but a matrix which is defined, which is orthonormal and defined in this sense. Only 0, right? Unless you have these kind of issues. If you have these kind of issues, you are going to get 0 otherwise, right? And that's what it is. What is the space, if you go back to what we initially had out here? What is the space? What is the set of vectors such to which basically correspond to the null space of it?
And z not equal to.
No.
That is for null space, right?
No. null space, xy not equal to 0, and z could be anything,
Oh, yeah.
right?
Z could be anything. The moment Z could be anything, it's done. Right? So XY can be anything.
Yeah, exactly. Sorry, yes. So for z not equal to 0, the entire space is now cannot be reached by this guy, right?
Yes.
So that
you
is
cannot span into any of the space where Z not equal to 0.
right. And so
Sorry, word wrong. Word rearrangement.
really, so there are two separate issues, right? One is the range and the other is the null space, right? So in the null space case, where is this going to be 0? Xy equal to 0.
Oh, okay. When in
That's the null space, right?
Z equal to 0.
The range is different. The range is wherever z is 0, that's the range.
Yes. In the range you want to check your null space. That is only when X equal to Y equal to 0, right?
No, x equal to y equal to 0 means that's the case where it is non-singular.
Non-singular, yes.
So for the non-singular case, the null space will be only x equal to 0.
Yes, right.
The moment you have some value which is where it's not 0, then basically the null space being anything besides the null vector,
Yeah.
then you have an issue with singularity. Is it clear? Which part are you having trouble with? Do you understand what I mean by null space? Okay, forget matrices for the time being, right? So when you start defining some sort of a space, so we have these identities that we are defining, right? That a times 0 is what? 0, right? You've assumed this. This you want to extend now onto matrices, or to basically, in a general sense, more vector spaces. In the standard case, when you talk about a times 0 equal to 0, you're talking of the real space out here, right? That a is some real number and times 0 is equal to 0. We want to extend this to vector spaces, the same concept. And here, of course, it's not as simple as saying that anything times 0 is equal to 0, right? So the question is that we are trying to say is that, is it possible that if you have matrix A times x equal to 0, what is the range of values such that this is true? Okay? The simplest answer is the same as what happens in your standard when you're considering scalar numbers, your real space. In which case that x equal to 0 always satisfies this. The question we are asking now is that, is it possible for a value of x other than zeros that a times x is equal to 0, right? And that's what the question was. So if you think again in the sense of the two-dimensional plane sitting in 3D space, right? And that's how we have decided that this is our matrix A now, correct? So it's a very, very simple case. It's like an identity matrix with the last entry being equal to 0. In this case, if this is A and this is X, and I put zeros out here, this is 0, correct? What happens if I put 5 here? It's still 0, right? Which means that the null space now has vectors in it which are not 0, right? So that is basically, so look at the definition, right? The null space of A is defined by all vectors x such that A of x equal to 0. That's just a definition. You just have to look at what it is. There are implications if the null space is not only 0. If the null space is anything but, is something which is not only containing this, then you have an issue. Okay? And that's what it is. And you can, if you look at this example, it tells you what it means, right? That we are not really sitting in three-dimensional space. If this was this matrix, what is the set of values where you will actually get 0? Only if all of them are 0. This is also true if I take this and I apply a rotation to this. Okay? Which means that you choose some combination which is rotated. So again, maybe a 2D example is easier because I can draw a 2D case. Say that we are talking of a two-dimensional matrix. So this is 0, 1, 1, 0, right? This space, these vectors, this is what? This is 1, 0, correct? This is 0, 1. Yes? So now if you put these together, you're going to get these two, right? So the columns are defining these axes basically, right? So if I have a point and I'm multiplying, that's giving me what the value is. You could now say that instead of this, the space that I'm actually concerned about is actually this. They're still perpendicular to each other, they're still normal to each other, but there is a rotation, okay? So this is now going to be, what is cos 45, sin 45? It's half, right? 1 by root 2. Okay, so then you're going to change this to being 1 over root 2, minus 1 over root 2, and 1 over root 2, and 1 over root 2, right? So you're going to get this. If you have a matrix of this form, and you now start multiplying this with values, what is the null space? Does it change? It's still going to be 0. Whatever you do, you're only going to get 0 if all of them are 0. And that's basically what you're defining now. Take that as an alternative to this case. So this is not true if I start looking at arbitrary matrices, right? If I start looking at arbitrary matrices which are actually going to be, let's say I do 3, 0, 0, 2, right? So these are not necessarily now exactly what you want, and so there you're going to have issues. Actually, maybe let me give you a slightly better example. So if I choose so if you did something like this, right, then a value of 1, 1 is still going to give you 0, 0, right? So those are bad examples. This is a case which looks like it's sitting in a high dimensional space, but in reality it has a null space which is not equal to 0, right? So that is the first set of values. The second set is that if I give you an arbitrary matrix now, and you want to look in terms of its columns defining a space, right? Each of those columns can be thought of as a vector, right? The x that I multiply this matrix by, so if I'm saying A times x and I've said that A is a set of columns, right? If you think in terms of these columns now, and this is x, right? And let's say x is going from x0, x1, x2, and so on. This is going to be just x0 scaling the vector a1, if this is a1, a2, a3, a4, right? Plus x1, a2, sorry, and so on, correct? This is the same concept as if you had a regular basis, your regular coordinates in x and y, right? It's how much of x, how much of y. Instead of that, you're saying that the vector x is scaling the columns of the matrix A. So this is defining a space. Now, that is the second concept which is related to the range of this matrix A. Assume that I can take any arbitrary x. Can I generate any b? It's kind of related to the first question, but it's not exactly the same. So now we are saying that can I, which is again, if you take sort of the 2D plane and 3D example, I can choose any value of x, but I will never get a point which is not z equal to 0, right? So it's the range of values which is possible by some arbitrary combination of the columns of A. That's all you're saying. If it is a value which can be obtained by some arbitrary combination of the columns of A, then that is the range of the matrix A. Okay? Clear? And that's what it is. And the rank, of course, is then the secondary part, which is what is the true dimension of the range of A. In that example that we talked about, it was 2D. If again now if you had a bunch of points like this, then you're going to end up with the rank of 1, even though you might be specifying a 3-dimensional coordinates for it, or even any arbitrarily high dimension, right? Because the variation that you observe is only along that one dimension. So by the choice of an appropriate basis or an appropriate line, which is along the dimension of variation, you will be able to characterize it perfectly, instead of having to specify it using X, Y, Z or so much of information. Go back to the way we argued initially about recommendation systems. We said that even though you have billions of users and then you have billions of items, in reality, there are a much smaller set of users and a much smaller class of items, which again says that basically is that it is more like a 2-dimensional plane sitting in 3D, and that's what we would like to figure out, right? Clear? Understand also that when we say that we want a lower rank approximation, so one way is that you can take your data, compute the SVD, look, exactly compute what the rank is. But now think of a case where you had, let's say this as a cable out here, right? Let's say this is in 3-dimensional space. I can go and specify, let's say the walls of this room specify your X, Y, and Z coordinates, right? They're the axes. So that is origin. So then I can have a set of points along this wire which defines, let's say a straight line out here, which define what my data points are, correct? Ideally, we might want to get the fact that it's a rank 1 matrix. This data is along one single line, right? It's a 1-dimensional thing, which means that all I need to do is to get the correct orientation for this, and then I can just say 0, 0.1, 0.2 till 1, and that defines all my data points, right? It's a 1-dimensional representation as long as I have the n-dimensional or d-dimensional eigenvector to specify it. Is it clear? So the first part just tells you how it is rotated, and then what is the variation within this. You could obviously say that maybe we don't want to do this, we can take this instead, and we are saying that I'm generating a low rank approximation, but this is not all the way to the 1-dimensional case. I might just get this instead, which is that I have approximated it by a plane, so now it is a 2-dimensional. It's still going to be a line in 2D now, but this is still less than what I started off with. So instead of having all of this space, we have reduced it to 2D, even though I could potentially, we're not. So when we take our recommendation systems and we're saying that we're generating something with D dimensions, that D might not be exact. It might be a bit of an overfit, but it's as long as it's significantly less than what we did, it's okay. You should also think in terms of the example that I showed, that you could represent it with fewer than that. So if you had your initial data, which was, let's say something like this, right? This means it's a line in 2D. And so we are going to represent it like this. But let's say that we actually had some variation out here, which is that it's primarily along this dimension, but there is a slight variation in the other direction as well. You can approximate this in 2D, or you can say that I'm just going to discard these. And I'm only left with a 1-dimensional data, which is basically then going to be the projection onto this line. So any points which are out here are going to be projected onto your primary eigenvector. In this case, we have lost some information. We started off with something which was two-dimensional. We've approximated it by a one-dimensional entity, and so we have lost information. Okay? And you can do this, and the amount of information loss is again now going to be proportional to what your sigma 2 is, because that's telling you what the spread is. So if sigma 2 was large and this was looking more and more like a circle, then you're losing a lot more information by dropping this out here. Okay? The information along this dimension. Whereas if most of the information is in this direction, then you're okay because you're not losing much. For really large problems where we don't have any direct idea of what the true dimensionality is, we are in some cases doing this, which is that we are estimating a lower rank than is in reality, and in some other cases we might be overestimating, which is basically that even though the true dimensionality might be of rank k, we are estimating k plus y or something. You're not really doing it correctly. But in both cases, we are greatly reducing the actual dimensionality that we have. Okay? And once you sort of understand these concepts, what you can do is to basically link it back to your SVD itself to figure out how, because how would you actually, for more complicated cases, figure out what the null space or what the range is if you wanted to characterize it? And that is what you're going to do from an SVD perspective. For simple cases, you have from an analysis of what you have defined as your actual basis, you can figure out. But for more complicated cases, this is what we're going to do. We're going to generate the orthonormal basis, and based on the orthonormal basis, we can figure out what the null space and the range of the given matrix are. So now let's look at randomized SVD. The randomized SVD is related to the standard SVD, but it's in cases where the matrix is so large that the cost of actually computing the direct SVD is going to be too expensive, or you cannot really fit all of it into memory. So we're going to be looking at cases where you have those kind of things. So it's too expensive. So can we actually, by some sort of a random sampling of the matrix, get an approximation which is close enough? And this doesn't work in cases where M is dense and is of full rank. But when M is of a sufficiently smaller rank, we can get an approximation. The other way to look at it is that we're saying that I agree that my data sits in some high dimensional space, but we are now going to look at the approximation or the projection onto a lower k dimensional space of my data. And so in this case, it's like saying that I'm generating my true SVD, making the eigenvalues beyond the rank k 0, and then looking at data only in this restricted space, the most important k eigenvectors. Okay?
Any case which dimension should we choose for setting their values to 0?
So you will not, that's not how it works. That is conceptually what your result is going to look like. So we are not randomly picking k eigenvalues and eigenvectors. We are choosing some k, and this choosing k, especially in this setting, is a very hard problem because you're now saying that I'm not going to look at all the data. I'm looking at some of it, but because of the nature, so why does it work? Before we get into it, try to understand intuitively why it works. What you're saying is that what we want to estimate is not k random eigenvectors or eigenvalues. What we are interested in is getting the k most important ones. It's the k largest singular values and the largest the singular vectors corresponding to those largest singular values. Correct? That's what we're interested in. But all this discussion that we had till now, we talked about where the singular values are giving you an indication of how much information is there. So if we are doing random sampling of data, then you're going to basically retain more and more information about the largest modes of variation as opposed to the smallest. Intuitively, that is, I'll derive this for you next time if you want. But you can actually prove that it is what happens, and you can give error bounds on how close you are to the real solution. Okay, so you can define variations, let's say the difference between the estimated eigenvalues by random sampling versus the actual eigenvalues. Okay? And you guys can play around with this when you implement it. So that's the general idea. So the general idea is that you want to randomly sample this data so that we can get an estimate for the largest eigenvalues in the eigenvectors, not some arbitrary eigenvalue. If you ask me to generate the 10th largest eigenvector on its independently, that's a very hard problem. Okay, so the reason that this works is for that. What exactly your K should be is a harder problem. So in this case, again, as with what we did, we talked about this when we looked at the UV decomposition, is that we're just going to pick K sufficiently large that we think it will be rich enough to have the level of complexity in our distribution that we expect, but at the same time it's small enough that it makes the overall problem computationally tractable, right? So you're basically balancing this out, and it's somewhat of a heuristic pick. If you have the luxury of loading all your data, or at least some sufficiently representative data, you can actually do a full SVD on it, look at the entire spectrum, the list of eigenvalues, and see where it's retaining most information. So you can sort of look at the energy norm of this and figure out that 90% of the information, let's say, is in the first 10 eigenvectors, or so we can then say that that's the rank that I want to approximate. But in a generic sense, you might not know, and the overall problem is so large that you can't. And so you can either do it iteratively and see how close an approximation you get, or you choose something which is computationally reasonable for you, and you just proceed with that. Okay? So we looked at a few other randomization that I'm talking about is coming from the number of K samples. So it's like, let's say it's just step 2, right? How many samples have you generated? I would rather generate a few more extra samples here than do the whole thing again a few times. Also realize from a parallelization perspective that steps 2 and 4, which are in most cases that the computationally dominant part, will permit a K-way parallelization. You're doing K matrix vector products, so those can be completely parallelized, and there are no implications. You're just independently doing it, so it's actually very easy. And this is immaterial whether you're doing a MapReduce style parallelization or you're doing an MPI style parallelization. If you're doing MPI, you could parallelize the actual matrix vector product itself. And that's why this is a nice algorithm, because it reduces your. So we need to define now what is an error metric here, right? How do we actually look at it? I'll put a paper online for those of you who want to go a little bit deeper into understanding what the origins of these numbers are. But at least you need to understand how you would measure something, an algorithm of this sort. So the error of the method is going to be defined in terms of the difference between the matrix A and the K-rank approximation that we generate from our randomized SVD, okay? And some norm of it. Now, if you say that, now EK, of course, is going to be a random variable whose theoretical minimum value, right, is sigma K plus 1. Is this clear or not? It's going to be bounded by the absolute minimum error difference that you can get is going to be related to the K plus 1 singular value, right? this is the place where we are chopping it off. So independent of anything, that is the level of information that we have discarded. So that's the absolute minimum, right?
But you're also combining them. You did not take the first n eigenvalues, right? You made a random. You choose random combinations of them, right?
I haven't chosen random. I've tried to.
No, when you did n cross k and multiplied a with n cross k, you
No, so-
took the different columns and multiplied with small
Yes.
property numbers and then multiplied it. Wouldn't the eigenvalues change a little bit because
They will change. They are approximations. The question is not on this. In the best case scenario, in the absolute best case scenario, I have accurately estimated the top k eigenvectors. So the minimum amount of and the top k eigenvalues. So the absolute best case scenario for me, the error is that it is sigma k plus 1, right? Because I have only k eigenvalues, so that's the minimum amount of error. This is in the case where I perfectly estimated everything else, right? Now, obviously, this is not possible, so our goal is that we want the actual error to be as close to sigma k plus 1 with a high probability, okay? This is what we would like,
Yeah,
but
If you do the SVD, the deterministic, you get this analysis. But if you do randomized,
no, this is the randomized, this is an approximation. Yeah. This is true only if you do the exact SVD, right? So in a randomized sense, the problem is that although we would like this to be close, the expectation of EK over sigma is very large and has a large amount of variation. So this would point to the fact that this is probably not a very good way of getting EK low enough, at least reliably. But you can prove that if you oversample a little bit, and by a little bit it's like usually 4 or 5 extra samples. So if P is some small integer, then you can bound EK plus P by something which looks more like this. Okay? Try to sort of somewhat ignore the actual values. The more important thing to notice is it really depends on the rate of decay of eigenvalues themselves. So as long as, so this goes back to what our original problem was, that if you have a situation where the true rank is low and it's decaying rapidly, then randomized SVD with a little bit of oversampling gives you a very good approximation. However, if you have a situation where you have some drop and then the eigenvalues flatten out, then this is not going to work very well. Luckily for us, in most cases, this is not true and the eigenvalues do indeed decay very, very rapidly.
yeah, that's very good point. But if we have a distribution that follows parallel, which is lots of data in real world, then this decay is just perfect, right?
It is. No, which is true. And that's what. So what you need to understand is that the reason I'm making this point, and for those of you who are interested, I can go over the proof. It's a very interesting proof. The reason you need to understand is that, again, I said this is a Swiss Army knife, but you need to know where to use it. So randomized SVD will work as long as your data has these characteristics. It's not just an issue of saying that, do I have a sufficiently low rank, but the more important factor in terms of using randomized SVD is to say how quickly does it decay out. Keep in mind, this is not a problem if you use the standard SVD, because in the standard SVD, I would get the top k eigenvalues, and that's an exact, it's not an approximation anymore. I shouldn't say it's exact, but yeah. But in this case, we are making an approximation, and the approximation is good as long as these terms, because of this summation term out here, it really depends on how quickly your sigma j's decay out. Okay? And I think that's the last slide.